Welcome to 39th lecture in the course of Industrial Engineering and Operations Research. We are discussing operations research, and in operations research also we are discussing the topic of linear programming problems. In the linear programming problems, we discussed the methods for solving the optimization problems by means of graphical method and also by simplex method. Then we also discussed how we can make a dual problem of a linear programming problem, and we said that in the dual problem decision variables are basically the unit worth of resources, you can say unit worth of constraints of the primal problem, of the main problem. So, we call them dual prices. These dual prices are very important. So, if you want to get a dual price, naturally there are ways you can get that idea from the simplex table also. You can get it by solving the dual programming problem. So, this one now can be also obtained by another method. Today I am going to tell one method of using Lagrange multipliers. Okay. You may not find this method in most of the operations research book, okay, because it is I am telling something different way. Maybe it is not that efficient way, but it is worth knowing this method also. This is, you will appreciate it in much better way because this is based on the concept of Lagrange multipliers. Okay. And this is often the topic of Lagrange multiplier you can get in your first year level book on the calculus, like Thomas Feeney book. In that you can find out this thing. So, sometimes we have say some problems like say I say maximize x minus 3 square plus y minus 5 square, but I says that subject to x plus okay, x plus y is equal to x plus y equal to 10. Okay. So, I say x plus y equal to 10. Okay. Maybe I write it in a better way, x plus y equal to 10. Okay. Now, this is a problem where you have to maximize objective function has been given, but there is a constraint also that suppose x plus y is equal to 10. You may have even another constraint also. It may be x minus y is equal to 6, like that also you may have. Then what to do that, how to solve that? By method of Lagrange multiplier, what we can do that we can write a Lagrangian function and we can say x minus 3 square plus y minus 5 square plus lambda times x plus y minus 10 plus mu times, mu is another Lagrange multiplier, lambda is a Lagrange multiplier, x minus y minus 6. This type of thing you can write, this is called the Lagrangian. Then in order to optimize it, maximize it, you can put the condition, necessary condition del L by del x equal to 0, del L by del y equal to 0, and then you can say del L by del lambda equal to 0 and del L by del mu equal to 0. By solving these, you can get the values of not only x and y, and you can get the values of lambda and mu also, which are called Lagrange multiplier. Okay. This topic is explained in the book of the calculus also, but here I am not giving derivation, but I am just telling the procedure that is how you can find out Lagrange multiplier. Now, Lagrange multiplier, they have the significance, they are in fact the unit worth of resource. So, unit worth of resource will be given by the Lagrange multiplier corresponding to x plus y equal to 10, that will be given by lambda, and unit worth of resource of x minus y is equal to 6 type of constraint will be given by mu. So, using this concept, let us see how we can get some idea about dual price. It will give you some another method to cross check your answers. Okay. So, let us go to that next slide. Okay. So, to start with, let us take one example, and this example problem is that product M1 requires 1 kg R1, R1 is some resource, and 2 kg of R2. 1 unit of M2 requires 3 kg R1 and 1 kg R2. Maximum available R1 is 100 kg and maximum available R2 is 150 kg. So, profit of M1 is rupees 2 per unit and that of M2 is rupees 3 per unit. Formulate the problem. Now, how do we solve that? So, I am denoting product M1, but even its quantity also I am denoting by M1 only. You can use different symbol, you can use maybe X or you can use X1 for the quantity of M1, but I am straightway I am decided to use M1 as a symbol of number of units. So, what is our objective? We want to maximize the profit. Therefore, we say that maximize 2 into M1 because we get 2 rupee profit in 1 unit of M1. So, if I sell M1 unit, I will get 2 M1 money and then plus 3 M2 because the second product's price is 3 per unit. So, we get plus 3 M2. So, this is the maximization. Then subject to M1 plus 3 M2 smaller or equal to 100. Why? Because for making 1 unit of M1, I need 1 kg of resource R1 and 3 kg of resource R2. So, that means 1 M1, oh no, first this is 1 unit of M1. Okay. Suppose I concentrate on resource 1 first. So, resource 1 requires 1 kg of 1 kg. So, product M1, 1 kg resource is needed for making 1 unit of M1. So, if I make M1 unit, so I need 1 M1 unit kg of resource, and then similarly I need 3 M2 kg of resource R1 because each unit of M2 requires 3 kg R1. So, total resource needed for this purpose is M1 plus 3 M2, that much R1 is needed. Okay. So, this is R1 and this should be smaller or equal to 100 because we have only 100 kg of resource. And then similarly, as far as resource R2 is concerned, so I am 2 kg per R2 is needed for 1 unit of product M1. So, if I make M1 quantity, so 2 M1 is the R2 needed for product 1 and M2 is the quantity needed for product 2 because only 1 kg R2 is needed for making 1 unit of M2. So, 2 M1 plus M2 is the total consumption of R2 and it should be less or equal to 150 because our constraint is that availability is only 150 kg and M1 M2 is of course greater than 0 because you cannot make negative quantities. So, this is must that you should write like this. So, this has become a problem. Now, why unit worth of resource or dual price is important? Because you want to know that suppose I increase R1 by 1 unit. Let us say we have 100 kg, but now I make 101 kg. Then how much extra profit I can expect? Similarly, if I change 150 to 151, then how much extra profit I can expect? That will give the unit worth of resource of R2. So, unit worth of resource of R1 and unit worth of resource of R2 both are important for us. Okay. So, let us see that how we get or how we used to do that. So, here this is this one is like I make, suppose I want to solve it by dual method. So, I make the dual of that. So, dual making is very easy. We just have to say that minimize. Okay, here how can I can straightway make it here for you that I can write. In next slide you can see the final expression nicely written. Here I can write like this, that suppose I say minimize maximize becomes minimize, okay, minimize, and this will be say 100 R1, because suppose plus 150 R2. Let us say I denote this also by worth by R1 R2 only. You can use Y1 Y2 basically, okay. And subject to how do I do? I focus on coefficients of M1 to write the first constraint. So this is basically R1 plus 2R2, okay, and smaller it is greater than minimize. So with minimize, greater than sign will come, and greater than basically 2, and here it will be 3 R1 coefficient of M2, and then 2 R2 greater or equal to 3, and naturally R1 R2 greater or equal to 0, okay. So that type of, let us see that what we have written. So I said minimize 100 Y1 plus 150 Y2. I used Y1 Y2 symbol for that, and subject to Y1 plus 2 Y2 greater than 2, Y1 plus 2 Y2, and 3 Y1 plus Y2 greater than 3, Y1 Y2 greater or equal to 0. Then I can solve this problem graphically, okay. For solving graphically, in fact, graph etc. I try to take the help of computer, okay. You can make it in graph paper, but it is not a problem if you use that computer tools in a responsible way, okay. But you have to see that sometimes there can be mistakes. So I use that this site www.a2z-math.com. So I made the, I gave the problem, and then it made the corresponding graph of the problem by, and it solved the problem by graphical method. So let us see that how it did. Of course, that you know, on the x-axis this is written x1, but it is basically our y1 here, that y1, and this is x2 here written, it is there basically y2 axis, okay. So you know, first we make constraints. So constraint is y1 plus 2 y2 greater or equal to 2. If I make a line y1 plus 2 y2 equal to 2, suppose we make a line y1 plus 2 y2 equal to 2, then how to draw this line at y2 equal to 0, y1 equal to 2. So therefore at 2 I made a point, and if y1 is equal to 0, then y2 is equal to 1. So at 1 I made a point and join this line, red line, this has been joined, and this is one line. So you have to be greater than on that side, so that means you have to be away from this origin. So like that. Similarly, another one, 3y1 plus y2 greater or equal to 3. So y1 is equal to 1, I have written 1 point here, and y2 is equal to 3 if y1 is equal to 0. So therefore this point is also here, and I have drawn it like a green line, and this is another one, and you have to be away from that. So you have to be away from that. So therefore feasible zone came, what has been shown by hatched line. So hatched area is the feasible one, and now I have to minimize 100 y1 plus 150 y2. So how should I do that? If I can draw a line parallel to say something 100 y1 plus 150 y2, then that line can solve my purpose, okay. Maybe that I am telling that approximately the line may look like this, okay, if it is like this, and then I can keep it moving, and I will see that shortest distance will be at this point, okay. Here this distance, anyway this is not feasible region, that region is also too much far away, that point, okay. Optimum will lie only on these cardinal points, but this is far away, this is far away. So basically this line, this point gives me that the solution. So you know that by intersection of these two lines I get the solution. So one line is y1 plus 2 y2 is equal to 2, and another line is 3 y1 plus y2 equal to 3. If I intersect this, I will get y1 y2, and then my function value will be the minimum, okay. So now what happens that here if we do that in the software, it does like that, the value of the objective function at each of these extreme points. So they find out the extreme point. Now extreme coordinate points are A, that means there is a point A that which is written at 0, 3. So, 0, 3 means basically this point, this is A, this point is there, and another. So, at that point they say that what are the things points. So, intersection gives you these points basically 2 and 3, one line is x1 greater or equal to 0, intersection of these points gives you x2 is equal to 3. So, 100 into this, so 450. Similarly, intersection of these two lines gives 0.8, 0.6. So, this you gives 170, and then also they have done that C point, okay, basically C point, this is this one, this is C, that means this point is 20 and it gives you 200. So, we automatically see that by extreme point method we get the minimum value at 170. That is another method of that. You check the values at each and every kernel. Otherwise, do as I have told that this one basically make the iso lines, okay, means you make one sum line parallel to 100 y1 plus 150 y2 is equal to say maybe 100, okay, just this one, and then all parallel lines you can do that by minute after, and whatever are set square and whatever line you know that cuts this one, then you can see that this is the thing. So, I am moving it 100 y1 plus 150 y2 equal to C, that I am moving, and I am going up to here. If I go this one, it will be even further from you know that 0. So, its value will be more, and this is also far away. So, that is how that. But another method is that if you don't or you are not sure of making that line of objective function properly, or you can make mistake in making a parallel line, then you can go extreme point method. That means you see that how many kernel points are there, and at each kernel points you can calculate the value. So, here minimum value is naturally occurring at 0.8, 0.6, and this is z is equal to 170. So, therefore, optimum solution to the given problem is x1, okay, in our notation it is not x1, it is basically y1 equal to 0.8 and y2 equal to 0.6, and minimum value is z is equal to 170. So, y1 equal to 0.8 and y2 equal to 0.6 are the unit worth of resource. That means, if you increase 1 unit of resource 1, that means y1 plus 2y2 becomes equal to 3, then your objective function value will increase by this much amount, okay. That means it is not here, this is the y1 y2 here, not in this. So, unit worth of resource you have to find out by of this one, these resources, okay, because in the primal problem. So, dual variable was 0.6, suppose it is 0.6 there, because we have shown that y1, sorry, no, here y1 is equal to 0.8, okay. So, suppose y1 equal to 0.8, that means if I increase 100 to 101, then I will be increasing my profit by 0.8, okay. That is the meaning of that, okay. So, let us see that here how it happens. Now, if I can do it by Lagrange multiplier method, the same problem. So, if I want to do by Lagrange multiplier method, then I just pay attention that suppose maximize this much, and then I understand, okay, from LP problem that basically these two constraints will be active. That means, if you solve that problem, then active constraints are m1 plus 3m2 is equal to 100 and 2m1 plus m2 is equal to 150. These will be fully satisfied because solution will be obtained by solving these two type of this one problems, okay. So, therefore, you know that if you say it could have been that suppose some one constraint would have been inactive, then its unit worth of resource is 0. So, here both are active. So, let us say make the Lagrangian problem. So, if it is active, that means effectively this problem is equivalent to maximize 2m1 plus 3m2 and subject to m1 plus 3m2 is equal to 100 and 2m1 plus m2 is equal to 150. this is equivalent to that. Okay, we say that it is equivalent to, because these two constraints are active. Why that if I am not even writing m1 m2 greater than 0, because writing it or not writing doesn't affect anything. So because it is whatever solution is that is far away from 0 line. Okay, it is far away from 0 quantity. So therefore as if that constraint is not there. Okay, suppose I am in a room whose dimension is 10 meter, but I can move only from the central position. I can move because of some other constraint only 1 meter. So for me it doesn't matter, as if that constraint is not there. Those room, I am not in a room, I can consider that I am basically room is not putting any problem to me, because anyway I cannot move that much. Okay, so this is how that this equivalent problem has become, and then we write the Lagrangian function of that for solving that, using the any calculus books method like Thomas and Fanny or any other textbook. So L is equal to 2m1 plus 3m2, that is objective function, plus lambda 1, and I can say m1 plus 3m2 minus 100. You can also write 100 minus m1 minus 3m2, that sign actually only sign difference will be there, but I am writing this way, and lambda 2 is equal to this much. Then we say del L by del m1 is equal to this one, del L by del m2 I get 3 plus 3 lambda 1 plus lambda 2 equal to 0. Second equation, del L by lambda equal to 0, del L by delta lambda 1 is equal to 0, that is basically m1 plus 3m2 minus 100 is equal to 0. So we get back that constraint, and del L by delta lambda 2 is equal to 0, 2m1 plus m2 minus 150 equal to 0. We get back the another constraint, that is this one. Okay, we get back, but I am writing as a fourth equations. So now 4 equations, 4 unknown, we can solve them. If we solve that, we get m1 is equal to 70, m2 is equal to 30. So we see that if these two constraints are active, then we get the solution 70 and 30, that is the optimum one. And but we also get lambda is equal to minus 0.8 and lambda is equal to minus 0.6. So you see that they are the dual prices with sign changed. Okay, so therefore they are this one. So therefore dual prices are also called simplex multiplier, basically Lagrangian multiplier. So you see that here we got the dual prices like this, because that point was of this one. We have already said that x1 is equal to this, gives this one, and see here we were getting the solutions. Okay, so this is this one is like this. So when we solved that, we got hence the optimal solution of the problem. We got y1 equal to 0.8. Now here also we see that by simplex thing, that you see that you got the dual prices 0.8 and this one. So this way also you can verify. In fact, Lagrange multipliers are interpreted like that. They are basically unit worth of resource. In general, suppose you have function minimize fx equal to 0, x means x is a vector, this is x1, x2, xn, and subject to hx equal to b, h is equality constraint, hx, x1, x2, so hx can be written as b minus x, and you see that necessary condition to be satisfied for the solution of the problem is like this, del f by del xi plus lambda del h by del xi equal to 0, I is equal to 1 to n. That's what we basically have done. We have written a Lagrange function and differentiated with each variable, and we can write about that how if we change that dB to dh. Okay, this is the derivation part. Anyway, we need not go into much detail, but basically it comes dB is equal to df by lambda, or lambda is equal to df by dB. So interpretation of lambda is df by dB. Okay, sign difference you have to be careful, sometimes it can be here and there, because being equality constraint, I can say something like suppose x plus y minus 5, I can add this in the objective function, or I can add 5 minus x minus y, because equality constraint is anyway is x plus y is equal to 5, and if you put minus also, to minus x minus y is equal to minus 5. So therefore sign difference can be little bit, but you can easily understand that when the quantity increases or decreases, that even sign you will not do any mistake, because you even get the idea. Suppose this previous problem is there, how you can do the sign mistake, because you know that m1 plus 3m2 is smaller than 100. If I increase 100 by 101, naturally that means I have more quantity. So, my profit is going to increase only, it will not decrease. Okay. Anyway, so that way I am asking you to understand the things, but you know here I did lambda is equal to df by db. So, df by db means if I change b by 1 unit, right hand side by 1 unit, how much my profit changes. Okay. So, in linear programming, the dual price of a constraint, also known as the shadow price or Lagrange multiplier, represents the sensitivity of the optimal objective function value to change in the constraints right hand side value. So, you understand that correspondence is this. Sometimes in a hurry you may do that mistake. Okay. That means if you got the value in, if you solve the problem and you have design variables in the dual problem, they will correspond to unit worth of resource of the other problem. So, that cross connection is there. So, therefore, it is written like that. Essentially, it indicates how much the optimal solution value would change if relaxed or tightened the constraint by a small amount. So, basically what is Lagrange multipliers? In mathematical optimization, Lagrange multipliers are used to find the local maxima and minima of a function subject to equality constraint. So, this is used for only equality constraints, but as you know that a linear programming problem may have many constraints and many of them are inequality, but when we get a solution, usually 2 constraints or maybe 3 constraints will intersect at a point. So, therefore, as if other constraints are inactive, that type of thing can be considered. So, it can be converted into one problem where you have only equality constraints. So, in Lagrange multipliers effectively introduce a new variable, that is the multiplier for each constraint, allowing one to incorporate the constraint into the optimization problem. So, dual prices are crucial for sensitivity analysis. Okay. So, allowing you to understand how changes in resources or constraints might affect the optimal solution. So, these dual prices are crucial for sensitivity analysis. Okay. That means it is also called sensitivity analysis. It is a part of sensitivity analysis. That means how sensitive your solution or optimal solution is to change in the constraint. Okay. So, that means that is called sensitivity, that you know this one. If it is very high value, that means it is very sensitive. That means sensitivity will indicate you something. Suppose in the original problem, m1 plus 3m2 is smaller than 100 and you get some profit was 170 unit. But suppose you change 100 to 101, whether the profit will drastically change. If it drastically changes, that means your constraint is very sensitive. In fact, if you do numerical mistake here in writing 100, actual value was 99 and you wrote 100, then your result will drastically change. So, sensitivity analysis is very important. So, that is what Lagrange multipliers, they give the idea about the sensitivity, and this is what. So, dual prices are crucial for sensitivity analysis, allowing you to understand how changes in resources or constraints might affect the optimal solution. Okay. Now, let us do 1 or 2 simple problems. Okay. Suppose I on the Lagrange multiplier, in order to get confidence, okay, I will revise, because many of you might have forgotten this one, your Lagrange multiplier method, or maybe you might not have studied also. So, therefore, I am telling it again, recapitulating it. Suppose minimize x plus y subject to x plus 2y minus 6 is equal to 0. If it is given like that and I want to minimize that. Okay. So, it is this one. So, suppose we write the, you want to do by Lagrange multiplier method. So, we write first the Lagrange function. Okay. That is L is equal to x plus y objective function plus lambda times bracket x plus 2y minus 6. Then I have to put the necessary condition for obtaining maxima or minima. So, we do del L by del x is equal to 1 plus lambda equal to 0 and we get lambda is equal to minus 1. Again I do del L by del y is equal to 1 plus 2 lambda, because del L by del y partially differentiate with respect to y, you get 1, and if you differentiate that y again with lambda, you get 2 lambda, and this is equal to 0. So, we get lambda is equal to minus 1 by 2. So, you get two different values of lambda. So, del L by del lambda is equal to x plus 2y minus 6. That is obvious that if you partially differentiate with respect to lambda, differentiation of x will be 0, differentiation of y will be 0, differentiation of lambda will be x plus 2y minus 6, because this is the, you can say, coefficient of lambda. So, this is equal to 0, fine. That is all right, but I am getting one thing is giving lambda equal to minus 1, other is giving lambda equal to minus half. That means there is no unique value of lambda, it means there is no solution to problem. So, there is no solution, that means you are not able to, there is no lambda which satisfies all the equations properly. So, in fact, then in that case, this naturally there is no maxima or minima. In fact, it is unbounded problem. In fact, there is no, basically we are solving minimization problem. So, there is no minima also. So, minimum can, because, and we can see also, I am just doing solving it just for fun, but we can see that here if I want to minimize, so minimization can approach negative infinity, because I can take even x is equal to minus infinity and I can adjust y in that way, so that it becomes this one is equal to satisfied, or we can say that something, or even I can say like this, say suppose I can say that x is equal to 6 minus 2y, okay, I can put like that, and then if I put that value in the objective function, then minimize, it becomes minimize what, this is x plus y, okay. So, 6 minus 2y plus y, so minimize 6 minus y. Now, if you have been given minimize 6 minus y, that means a constraint I put in the objective function itself eliminated that, and then it becomes minimize 6 minus y. So, what is the minimization of 6 minus y? You can take y is equal to infinity also, and you can say that it is minus. So, there is no minima or maxima of this function, okay. Even if you take the derivative also df by dy, then it becomes minus 1, that means it will never become 0. So, anyway, let us do the other solution. Suppose we say maximize 3x plus 4y subject to x plus y is equal to 10. Again we write a Lagrangian function L is equal to 3x plus 4y plus lambda greater or equal to 10 minus x minus y, del L by del x is equal to 3 minus lambda equal to 0, which gives lambda is equal to 3. But if I do del L by del y, that is 4, differentiation of 4y is 4 minus y is equal to 0, and it gives you lambda is equal to 4, and then del L by del lambda is equal to 10 minus x minus y equal to 0, that means get back the constraint. Here also we do not get a solution. So, therefore, solution is here unbounded. Now, we can see that basically maximize 3x plus 4y is equal to 3x plus 4 10 minus x, because y is equal to 10 minus x. So, this is 40 minus x. As x is unrestricted, we can take as large a negative value of x as we wish, and it becomes unbounded. So, it gives something. So, this is equal to this one. So, like that we can actually, I have given only these problems, but you can actually solve other problems in which solution is existing, that I have done one in the beginning itself. Okay, now suppose there is a problem minimize z is equal to x1 plus x2 subject to x1 plus 2x2 is smaller or equal to 6 and x1 x2 unrestricted in sign. Suppose you have this type of problem. How to do that? So, since they are unrestricted, therefore, you introduce x1 is equal to x1 dash minus x1 double dash, where x1 dash is also some real number and x1 double dash is also some real number, and x2 also you do that not that they are real number, but x1 dash, x1 double dash, everything is greater than or equal to 0. So, you enforce that it is greater than or equal to 0 in LP problem, okay, to make it like a standard LP problem. And so, negative number is the difference of two positive numbers. So, standard form of the LP problem becomes minimize z this much and subject to this thing like that. And then you add, because they are basically, this is a constraint is inequality one. So, you add slack variable and you have added slack variable S1, and then you make a simplex table. Okay, I have made the simplex table. You can make the table in the Taha way, but this I used that online solver in the Google, and I got this table. So, you see that this is the reduced cost and this is the coefficient. Here you can see variable x1 prime should enter the basis, but all the coefficient in x1 double dash column, okay, are negative or 0. So, x1 dash cannot be entered into the basis, hence the solution to the given problem is unbounded. So, it is also the case of unbounded one. So, by simplex method also you can know that the solution is unbounded, and naturally in that case, as I told, that if you see that below in some column, if all the coefficient will be either negative or 0, that means you cannot find out leaving variable. So, therefore, the solution is unbounded. So, naturally the solution is unbounded. So, now you understand the importance of, in fact, that greater than or equal to sign, because here the variables were unrestricted. That is why this problem is coming. If I constrain the variables, then of course that you can maybe find the solution, but in this case x1, x2 are unrestricted. So, in minimization even I can take equal to minus infinity also, but suppose it would have been that x1, x2 greater or equal to 0, x1 greater or equal to 0, x2 greater or equal to 0, then it will not be unbounded, because minimum value cannot be less than 0. So, minimum value will be 0, obviously it can be 0 in this case, because if you take 0, 0, it satisfies the constraints also. Okay. So, this much today. So, I have told today one method of solving the unit worth of resource, or obtaining the unit of worth of resource by means of Lagrange multiplier. Okay. So, we will meet in the next class. Thank you.